Continuing with our investigation into dynamics, we're going to yet use another sort of way of looking at things in Chapter 15, which is to approach problems from the standpoint of impulse and momentum. So I always like this example of impulse is, the idea of hitting the baseball with a bat. You know that the ball is coming at you, and when you hit it with the bat, obviously you're exerting a force on it. The ball changes direction and actually goes goes quite quickly in the other direction. And all of these are interrelated. What we're thinking about is we can think about the force that the bat exerts on the ball. How long is it happening? That would be the impulse. And we can also think about the change in the momentum of the ball itself. Obviously, it changes its momentum because first it was going this way, and when it is hit, it actually is going that way. So we get the idea of impulse and momentum when we start with the equation of motion, which we also call Newton's second law, where sum of forces equals m mass times acceleration. So going from that point of view, the sum of the forces equals m dv dt. We can do a separation of variables. And if we integrate from time equals some initial time of 0 to some arbitrary time t, our initial velocity would be v1 and our final velocity would be v2. So over here, we're just going to keep that impulse integral. This will end up to be the change in the momentum part. And so we call this the impulse, because what we're talking about here is that there's a force exerted on an object for a certain amount of time, and when we look at the sum result of that, that equals the change in momentum. We'll use linear momentum because that's what we're really looking at, although a lot of times we just drop the term linear. And so often this is called the principle of impulse and momentum, or the impulse-momentum relationship. And this is where we started when we studied collisions in general physics. And we're going to still come back and look at collisions, but sort of, again, having a little bit more tools in our toolbox as we do that. So like I said, we call this the principle of impulse and momentum. I didn't have vectors on my velocities on the last slide, and I should have, likewise on the force. And so there are certain situations where this type of approach is really going to be useful. If we're given the amount of time that a force is applied, or we're given a graph of force versus time. Also, look when we just want to look at changes in momentum or changes in velocity. So there's lots of different cases where this type of approach really seems to fit the best. This is the part I hate, where your book uses a different notation than we're used to. In our mechanics book, they call linear momentum. They denote it with a capital L, which is not how we're usually used to it. It's equal to m times v. It is a vector because the velocity is a vector. Of course, mass is a scalar. The units of momentum are going to be kilograms meters per second or slug feet per second. Momentum never got its own unit. So sometimes when we look at this relationship, the sum of the forces over time, integrated over time, is equal to the change in momentum. What we concentrate on really sometimes depends on the way that the information is given to us. For instance, and also recognizing that this is the impulse. Maybe we are given a graph of the force and how it acts over time. And then we recognize that the impulse is actually the area under that curve. And so we might be able to find the impulse, therefore the change in momentum, by using that graph. If that, if it's a constant value, the impulse is just the value of the force times the time, or sometimes we can use, an average value for the force if we don't have a functional relationship for the force, and so say that the impulse is F average times the delta time. One of the ways that we can rewrite the impulse-momentum relationship, which might be kind of nice to think about conceptually what's happening, instead of writing it as like here, where we're looking at just the impulse equal to the change in momentum. In this part, what they've done is they've added, well actually they've moved this over to this side and saying, okay, if I initially have an object that has this momentum and then an impulse acts on it, so here we see this on this diagram, so initially our object is moving up and to the right, and then there's some sort of force that's exerted on it for a certain amount of time that basically contributes a momentum, or impulse if you will, that's downward and a little bit to the right. And so what ends up happening is we end up with this final momentum here, where you see that this is literally has been pushed down and given this net final momentum. So I do sort of like this way of stating it because of the fact that it allows us to think about what's happening. We begin with a momentum. Some impulse is exerted on our object, which results in a new momentum after that happens. Because this is a vector, we can break this down into component form. And so in Cartesian coordinates, this is going to have three different components, an x, y, and a z. And the impulse and momentum relationship is going to apply for each one of those directions. One of the things that we use impulse and momentum for, well, actually how we derive the conservation of momentum, is to think about a system of particles. And so in this picture, they're showing you a bunch of different particles. The particles are sort of named by the subscript I. So we have maybe n particles where I goes from 1 to n. But for each particle sub I, there are actually two types of forces acting on it. We have internal forces. Those would be forces internal to the system. Basically, particle J exerts a force on particle I, and particle I exerts a force on particle J. There are those action-reaction pairs. Those are always going to be canceling out, those internal forces. If we look at the whole system, if we summed up all the forces, the internal forces are going to sum to 0. But there's also the possibility that each object may have some external forces acting on it. And in this picture, they're designated by the capital F. And so those would be forces that are external to the system, like gravity would be an example, or a push or a pull or something like that. And so when we look at the system, even though we're adding up over all the particles, notice that we don't see any term that involves the little internal forces, because those sum to 0. And so really our impulse momentum relationship remains identical for our system of particles. This is another time where we can just sort of think about the idea that if we have a system of particles, we can describe them in terms of the velocity and the position of the center of mass. And notice that when we're finding the velocity of the system, the overall system, we're looking at the total linear momentum of the particles divided by the total mass. Likewise, we can have the position of the center of mass. But what we want to do next is, and to finish up, is just use this impulse momentum relationship for a system of particles to actually get the result of the conservation of momentum. And so what we're basically saying is we have a system of particles, but we're saying the sum of the external forces is also zero. That is, either everything is in equilibrium, we don't have to worry about the external forces, and then as a result what happens is your sum of your initial momentum is equal to the sum of your final momentum. Should I use a 1? And so that's the conservation of momentum, is basically when there's no net external forces acting on the system of particles, what happens is then we can say that the initial momentum is equal to the final momentum. And this is really just conservation of momentum. We find that this is really useful for looking at what we view or call collisions, two objects interacting, and looking at their initial momentum and then their final momentum, and use that to find, say, the speed or the velocity of one of the particles given other information. And that's it for this first part of this chapter.